Alright, looks like we are live. Okay, so let's continue. Let me open the table of content first. Okay. Alright, okay, we are on chapter 6 and we are on homework measurement now. Let me check that. Alright, previously I am, what is it called? I am kind of curious. Is calling a function consider a context switch or not? This is the one, switching between process, right? There's this thing called context switch. Where is it? This one. If the decision is made to switch, the operating system can execute a low-level piece of code which we refer to as a context switch. A context switch is conceptually simple. All the operating system has to do is save a few register value for the currently executing process onto its kernel stack, for example, and restore a few for the soon-to-be executed process from its kernel stack. So I'm kind of curious if context switch, what is it called? Is calling a function consider context switch too, like switching between function. And there is this Stack Overflow answer or question, I guess. Let me put this in the chat, or you can check the description too. I put this here and other resource there in the description. Okay. Is it considered context switching because I save register before go to the function? Okay, no context switch occur when the kernel swap a process. Calling a user space function will leave you inside the same process. Okay. And therefore won't be context switch. Calling a kernel function, however, requires an operating system from the kernel, and therefore it is a context switch to the kernel. Okay, so maybe context switch in this case only happen when we call system call function, something like that. Maybe. I mean, I'm still not really sure how to check the context switch process, something like that. So yeah, that is something to keep in mind. Okay, I think I already read this before. Just run the program you want to run, okay? To limit what process can do without operating system assistance, like baby proofing. Okay, are we back? I hope so. Why did my internet connection suddenly disconnect? Okay, I remember reading this. Reboot the machine. Okay. Reboot is useful because it moves software back to a known and likely more tested state. Reboot also reclaims stale or leaked resource, for example memory, which may otherwise be hard to handle. Finally, reboots are easy to automate. For all of these reasons, it is not uncommon in large-scale cluster internet service for system management software to periodically reboot set of machines in order to reset them and thus obtain the advantage listed above. Thus next time you reboot, you are not just enacting some ugly hack, rather you are using a time-tested approach to improving the behavior of a computer system. Well done. I mean, yeah, I'm also curious because I've seen some difference between rebooting an operating system and shutdown and then turn it up again, So what is the difference between reboot process and shutdown and manually turn on the computer again? Is there different kind of state? Maybe, but yeah, I'm not sure at the moment. There's a lot of things that I'm not sure about, and maybe we will find that out later on. We will see. How long context switch take? Another question you might have is, how long does something like context switch take, or even a system call? For those of you that are curious, there is a tool called LM-Benz, right? Maybe I will take a look at this, but not sure when. That measure exactly those things, as well as a few other performance measures that might be relevant. Results have improved quite a bit over time. Roughly tracking processor performance. For example, in 1996, running Linux 1.3.37 on 200 MHz basic CPU, system call took roughly 4 microseconds. Okay, and a context switch roughly 6 microseconds. Modern system perform almost an order of magnitude better with sub-microsecond result on system with 2 or 3 GHz processor. It should be noted that not all operating system action track CPU performance. As Osterhout observed, many operating systems are memory intensive and memory bandwidth has not improved as dramatically as processor speed over time. Thus, depending on your workload, buying the latest and greatest processor may not speed up your operating system as much as you might hope. That is something to keep in mind. Okay. Alright. wait. Okay. Yeah, that is weird. I'll be back. Yeah, one of the problem of doing live streaming is that my internet connection suddenly disappear, suddenly down. Okay. Key CPU virtualization term mechanism. The CPU should support at least two modes of execution: a restricted user mode and a privileged non-restricted kernel mode. Okay. So it is from the CPU, the hardware, I assume. Yeah, I'm monitoring my internet connection too. It is from the hardware, I guess. The user mode and kernel mode, maybe. Okay, I'm not sure yet. Typical user application run in user mode and use a system call to trap into the kernel to request operating system service. Into the kernel to request operating system service. I'm not sure what trap in here means, like what is the trap instruction or something like that means, Okay, maybe we will learn that in scheduling, I guess. Maybe. I mean, I'm not sure yet, but that is something to keep in mind. The trap instruction save register state carefully. Change the hardware status to kernel mode. Okay, the hardware status to kernel mode and jumps into operating system to a pre-specified destination, the thread table. If you take a look at this, see, during the boot time of operating system, I assume we initialize the thread table and then passing that to the hardware. I'm not sure which hardware saving the thread table here, but yeah, the operating system initialize a thread table and the hardware save that. Which hardware it is, I'm not sure yet. Maybe the CPU. Again, I'm not sure which hardware saving the thread table that generated by operating system. But yeah, the trap instruction save register state carefully, change the hardware status to kernel mode, and jumps into the operating system to a pre-specified destination, the thread table. When the operating system finishes servicing a system call, it returns to the user program via another special return from trap instruction. Okay, I'm assuming this is, what is it called? Some kind of callback, maybe something like that. Again, I'm still not sure. This might be wrong, My assumption might be wrong. Okay. Where are we? Okay. Hold on a minute. Why my internet connection is unstable? Oh my god. If the frame rate drop, then yeah, I can understand, I guess. But suddenly lost connection. That's weird. Okay. Which reduce privilege and return control to the instruction after the thread jump into the operating system. Okay, return from thread reduce the privilege from kernel mode to user mode, and returns control to the instruction after the thread that jump into the operating system. The thread table must be set up by the operating system at boot time and make sure that they cannot be readily modified by user program. All of this is part of the limited direct execution protocol, which run program efficiently but without loss of operating system control. Okay. Once a program is running, the operating system must use hardware mechanism to ensure the user program does not run forever, namely the timer interrupt. Oh, so is the timer interrupt came from the hardware? I mean, again, is it some kind of default timeout that's set up by the operating system? I'm not really sure. Yeah, what is the interrupt timer here? I mean, I know that it will interrupt the process with a specified time. I mean, it is a timer, right? Can start timer interrupt CPU in X millisecond. But are we the one who set up the timer, or maybe there is some default timer from the timeout from the operating system, or maybe from the CPU itself. Yeah, I'm still not sure about that. Okay, once a program is running, the operating system must use hardware mechanism to ensure the program does not run forever, namely the timer interrupt. This approach is a non-cooperative approach to CPU scheduling. Okay, maybe it is from the CPU. Yeah, I'm not sure where we set up the timer for the timer interrupt here. Something to keep in mind again. Sometimes the operating system during a timer interrupt or system call might wish to switch from running the current process to a different one, a low-level technique known as context switch. Okay. During a timer interrupt or system call, make wish to switch from running the current process to so the context in here means process, I assume, right? Again, considering this Stack Overflow answer, when the kernel swap a process, okay, can switch between multiple things, okay, virtual memory area, oh, okay, but then is switching between parent and child process also considered a context switch? My hypothesis is that it is, because it is different process and have different, what is it called? Memory space, something like that. Again, I might be wrong, but for now, maybe switching between parent process and child process also consider context switch. Maybe. Okay. Wait a minute. I think I want to check this out. Okay. 90. This one. Why are no operating system getting faster as fast as hardware? In case you want to check, this is the paper title, I guess. You can check this out. Aside measurement homework. Okay, this is new type of homework so far. So far we have tried the homework simulation, right? It is running a Python script, something like that. And then homework code, it is trying out, what is it called? Trying out some of the process API like fork, wait PID, and variant of exec VP, execl, execle, something like that. Basically, in homework code, we are creating a source code to answer the homework question here. So what about the homework measurement? Measurement homework a small exercise where you write code. Okay. You write code to run on a real machine in order to measure some aspect of operating system or hardware performance. The idea behind such homework is to give you a little bit of hands-on experience with a real operating system. Okay. So maybe it is similar to homework code, but the goal is to measure some aspect of operating system. But we will write code again. Okay. In this homework, you'll measure the cost of system call and context switch. Measuring the cost of a system call is relatively easy. the cost of system call is relatively easy. For example, you could repeatedly call a simple system call performing a 0-byte rate, okay, and time how long it takes. Dividing the time by the number of iterations give you an estimate of the cost of a system call. One thing you'll have to take into account is the precision and accuracy of your timer. A typical timer that you can use is get time of day. Let me check that. Oh, okay. Interesting. Function get time of day and set time of day can get and set the time as well as a time zone. Okay, we're using time for second and microsecond. Okay. Read the main page for the tile. The manual page, this one. What you will see there is that get time of day returns the time in microseconds since 1970. However, this does not mean that the timer is precise to the microsecond. Measure back-to-back calls to get time of day to learn something about how precise the timer really is. This will tell you how many iterations of your null system call test you'll have to run in order to get a good measurement result. If get time of day is not precise enough for you, you may look into using the RTTSC instruction available on x86 machine. I'm assuming this is assembly stuff. Yeah, I'm not really sure what RTTSC. Instruction on X. Rhythm spell. Oh. Rhythm stem counter. Okay, now how to read this instruction? Is it exist in the main page? Nothing. Okay. Let me put this in the chat too. Is anyone wants to take a look? Yeah, I'm not sure how to execute the RTTSC here. Okay, measuring the cost of a context switch is a little trickier. The LM benchmark does so by running two processes on a single CPU and setting up two unique pipes between them. A pipe is just one of many ways processes in unique system can communicate with one another. The first process then issue a write to the first pipe and waits for a read on the second. Upon seeing the first process waiting for something to read from the second pipe, let me read it again. The first process then issue a read to the first pipe and waits for a read on the second. Upon seeing the first process waiting for something to read from the second pipe, the operating system puts the first process in the block state waiting for something to read from the second pipe. The operating system put the first process in the block state and switch to the other process, which reads from the first pipe and then writes to the second. When the second process tries to read from the first pipe again, it blocks, and thus the back and forth cycle of communication continues. By measuring the cost of communication like this repeatedly, LM bands can make a good estimate of the cost of a context switch. Oh, okay. So yeah, maybe the parent, what is it called? Switching between parent and child process using fork is considered a context switch too, because again it is different process, right? Parent process and child process. Okay, interesting. You can try to recreate something similar here using pipes or perhaps some other communication mechanism such as Unix socket. One difficulty in measuring context switch costs arise in systems with more than one CPU. Measuring context switch costs arise in systems with more than one CPU. What you need to do on such a system is ensure that your context switching process are located on the same processor. Okay, I'm assuming this one CPU in here means like one AMD CPU or one Intel CPU, something like that. So the one physical CPU rather than the core in the CPU. Again, I'm still not sure if it is one core in the CPU, then yeah, we might find that trickier, is that the word, on such a system. But it is one physical CPU rather than one core CPU, then yeah, okay. Maybe it is a little bit easier. But again, I'm still not sure how to do that. Fortunately, most operating systems have calls to bind a process to a particular processor. On Linux, for example, let me hide this first. The set affinity call is what you are looking for. Set affinity. Let me check that. Affinity, okay. Oh, wait, is it not a POSIX standard? Not in the POSIX standard? Or maybe specific to Linux? Set and get a thread's CPU affinity max. Wait a minute, a thread. So is one CPU means one thread in the CPU hardware? Yeah, what is the definition of one CPU there? Determine the set of CPU on which it is eligible to run. By ensuring both processes are on the same processor, you are making sure to measure the cost of the operating system stopping one process and restoring another on the same CPU. Okay. Yeah, I think this is a tricky homework, but let me check here. CPU mechanism. CPU API, CPU intro, CPU sketch, CPU sketch lottery. There's no CPU mechanism. Okay. Let me check chapter 7. Oh, CPU sketch is chapter 7. I'm not sure if you can read this. Oh yeah, not that one. Yeah, CPU sketch is chapter 7. CPU sketch MLFQ chapter 8, this one. The I click wait here. And then the lottery, okay. Multi-CPU scheduling, okay. So yeah, in the OS tab homework, we don't have any script. Cancel. So we need to write the code ourselves. Okay, get time of day. It's gonna take a while again. A step. Okay. Yeah, there is a box in Tmux 3.6 and 3.6a, which already been solved or fixed, but Arch Linux haven't picked that up yet. So there is that. a simple system call, 0-byte read. 0-byte read. If count is 0, read may detect the error described below. A read with a count of 0 returns 0 and has no other effect. Okay. Okay, what is the error here? On success, number of byte read is returned. It is not an error if this number is smaller than the number of byte requests. Fewer bytes are actually available right now. An error -1 is returned. Okay. Let me try that. Chapter 6. Let's call this h.c. I mean, we only have one homework, right? But yeah, this homework looks difficult for me. But well, let's try this out. Context switch. So I assume there is two questions here. Cost of system call and then cost of context switch. So system syscall. Let's use this one. Cost of context switch, I guess. Chapter 6. Okay. Read. File descriptor. Let's go. Okay. Like this. STT-in maybe file now. And then okay, something like this. settings. Let me try compiling that extra. Alright, I forgot adding test of lag because this is supposed to be the output file rather than the file that we need to compile to, right? Okay, so it looks fine. And now how do we use this? Get time of day. Wait, what? It is deprecated. Okay, interesting. Set time of day also deprecated. So what is the alternative here? Let me check. Get time of day. And it says a number of API that can be used. Time, okay. Deprecated or obsolete. I couldn't find the reason behind this deprecation. But the former rather than the latter was declared obsolete. This one. The POSIX standard, which has evolved over the years, these functions are taken directly from the POSIX specification, which have marked them as obsolete. Oh. Okay, so POSIX already marked this API as obsolete. For this reason, they are all not secure, not portable, have unspecified or undefined behavior, have tricky edge case. Better alternative exists. The application of API. There is no general law. Clock set time. Ceiling get standard. End of time. The time function will be used until the end of time. Okay. Is a POSIX function and POSIX standardized existing practice. Sometime GlockGetTime was invented with greater resolution and to be more portable because a better and safer alternative exists. POSIX noted that its obsolescence. Is that how you pronounce this? I think the note is pretty self-explanatory to a developer. So use GlockGetTime function instead of obsolescent getTime of the GlockGetTime. Since Linux 4.3, set time of the time was made to set the time. Okay, the history here, but not set time of the market time of the as obsolete, recommending the use of GlockGetTime instead. Okay. Let me put this in here. Check clock. How do we do that? GlockGetTime. Is there any example here? Time.h. And set the time of the specified clock ID. Let me check if there is example. The dynamic clock ID. Like what? Do we need this one? Maybe not. Okay, let me check. GlockGetTime clock and then the time spec. Clock real time. You know what? Maybe let me open this in here. Examples. Okay. time series. Okay. Now let's take a break first. Okay. Don't forget to drink water. Let me read this. REST and TP are commander time spec. Clock ID struct time spec. Okay. Struct time spec. Which to act is the identifier of the particular clock on which to act. A clock may be system-wide and hence visible for a process or per process if it measures time only within single process. Okay. Let me try this example here. Clock time X on shell rest resolution. Okay. Where is it? Shell rest. Oh, print resolution. What is G again? I mean T is for the integer type, right? What is G? set. Oh, a following integer conversion correspond to an inmax t or u inmax t. Okay. Second, okay. Is negative. You need to compute using the whole second as well as the nanosecond in general. The second. Theory. Actual resolution. What is good res gain? Find the resolution precision of the specified clock ID and if res is not null. Okay. Delta. Oh, I guess we started in delta. Okay. Actual resolution is another issue. So should we use clock get rest? Maybe. And cannot be configured. The resolution of clock depends on the implementation and cannot be configured by a particular process. If the time value point to by argument dp of clock set time is not a multiple rest, then it is don't get to a multiple of rest. Yeah, I'm kind of curious how to use clock get rest. Okay. Clock T. Oh, is this the casting? Okay. On Solaris, but on Linux. RTL library. Oh, this one. Since glibc 2.17. Okay. I mean, what is this? Clock real time, clock monotonic. What is the return value can -1. Clock address -1. With clock address, clock ID, and the rest, I guess, stored in the structure spec. Time spec rest clock real time rest, right? Okay, it is a macro maybe. Time spec, okay. TV sec and TVN sec. Maybe something like this. I kind of forgot the formatting here. Oh, long in, okay. something like this. I want to make the output something like this, and I kind of forgot. Okay. It is one. Okay, 1 nanosecond, I guess. So what is the clock restore? Precision. Clock real time. Okay. Clock monotonic. Yeah, I'm not really sure. I'm not really sure how to. I think we need UniSDT, right? SDT. Interesting. Within the current second, it ranges in theory between. Okay. Actually, solution is not an issue. Microsecond. Okay, so or maybe it is an enum. Well, anyway, let's try this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.